I'm going to show you how to find the direction of a magnetic field that results from moving current, and I'm going to show you how to find the force on a charged particle based on a known magnetic field and the motion of the charged particle. So in our first question here, find the magnetic field. Now it's called the B field. B is the letter we use to indicate a magnetic field. Now we've got a battery, and that battery is going to induce a current or cause a current to go through this wire this way. So I have a current going this way through the wire. To find a magnetic field, we use the right hand rule. So you make sure it's your right hand that you're using. You take your right hand, and if you point your thumb in the direction of the current, your fingers, when curled, will point in the direction of the magnetic field. So just turn your page. My current is going this way, so if I point my thumb, now make sure it's your right hand. If I point my thumb in the direction of the current, my fingers will point in the direction of the magnetic field. So my fingers here are pointing into the page, and we indicate into the page with crosses. So my magnetic field, as a result of the current in this wire, is going into the page on this side. However, on this side, see how my fingers would curl around, and on this side they're coming out of the page. We use dots to indicate a vector that's coming out of the page. So the magnetic field, as a result of this potential here, which causes a current to go this way, is magnetic field lines coming out of the page along here and going into the page along there. I determined that by using the right hand rule. You take your right hand, point your thumb in the direction of the current, and your fingers will point in the direction of the magnetic field. So notice above the wire they're pointing out the page, and below the wire they're pointing into the page. Now in the second question, we have a coil. And if you have a coil, you still use your right hand, but the current and the magnetic field switch spots. So your fingers can represent the moving charge in the coil, and then the thumb on your right hand is going to indicate the direction of the magnetic field. So with this coil here, see how the current is going this way? So my fingers are going to go this way in the direction of the current on the coil, and now notice my thumb is pointing up. So that means my magnetic field lines are coming out of here. So this is my magnetic field going this way. Now, magnetic fields exist in dipoles, which means the magnetic field lines are coming out of here and they're going into there. So they're going to wrap their way around and come back in. It's going to wrap its way around here and come back in as well. Now this is what always happens with magnets. And you're looking, perhaps saying, well, it's not happening there. Well, actually it is. See here, the magnetic field lines are coming out of the page. They would wrap around, go back in, and then go out that way. Magnetic fields always act perpendicular to the moving current. So we always end up with a three-dimensional situation. You can't analyze this fully in 2 dimensions on the paper. It's never going to be a complete view. That's why we have, in this case, current that's making its way out and around in that coil, and in this case we have magnetic field that's coming out of the page here and going into the page there. So again, to find the magnetic field, use the right hand rule. Make sure it's your right hand, and if you point your thumb in the direction of the current, your fingers will point in the direction of the magnetic field. Or if you have a coil, you point your fingers in the direction of the current and your thumb will point in the direction of the magnetic field. One thing to watch out for, if you're answering a question where it's talking about an electron, remember an electron has negative charge. So if an electron is going one way, you understand that as having current that's going in the other direction. So let's say we have an electron going like this. That's the same thing as having positive current going the opposite way. So make sure you get that right when you're applying the right hand rule. Now, let's say we have a question here where we're finding the force that acts upon a charged particle that's in a magnetic field. Now, to find the force on a charged particle, we use the left-hand rule. So make sure that it's your left hand you're using. And I've written on my left hand, we've got force. That B stands for the magnetic field, and the I stands for current. And this works like this. So you position your hand this way with your index finger pointing forward. Your thumb will point in the direction of the force, while your index finger points in the direction of the magnetic field, and then your middle finger points in the direction of the current. If you forget which one's which, because you don't have it written on your hands, just remember you start at your thumb and think FBI, like that police organization in the States. FBI. Force, magnetic field, current. But make sure you're using your left hand when you're finding force. Use your right hand to find the magnetic field that's a result of current. You use your left hand to find the direction of the force based on knowing the magnetic field and the current. So let's just apply this to a couple of questions here. So find the force on this particle. So I've got a P and a plus. That means that's a proton. So we've got a positive charged particle here. It's going this way, and the magnetic field is going upward. So I'm going to take my left hand, and I'm going to point my thumb. My thumb's going to tell me the direction of the force. I'm going to point my index finger in the direction of the magnetic field, my middle finger in the direction of the current. So notice here, my magnetic field is going up, so that's my index finger is going up. My current is going to the right, so my middle finger will go to the right. And when I do this, notice my thumb is pointing up, out of the page. So the answer here is that the force is going to be coming out of the page. If my magnetic field is up and my positive charged particle is flying through it that way, it's going to receive a force pushing it out this way. Okay, now here I've got an electron, so that's a negatively charged particle, and that dot means it's flying this way, it's flying out of the page, and I've got a magnetic field that's going forward. So again, I'm going to take my left hand, my magnetic field is going forward. Now my current, which way is my current going? That's an electron, which is a negatively charged particle. So if it's going out of the page, we understand that as meaning we have positive current that's going into the page. Because that's negative, the actual current is the opposite direction of the motion of that negative particle. So my current is going into the page, and that's my middle finger. My index finger, which is the magnetic field, is going to the right. And notice when I position both of those, my thumb is pointing down. That tells me that the force on this electron that's moving out of the page as a result of the magnetic field pushing this way is going to be downward. So I've got F, B, and going into the page, I. And again, a dot means coming out of the page, but if an electron's flying out of the page, that's current going into the page. So that means as the electron flies out, it has a downward force, so it's going to travel in a curved path like this. And that's actually how they find the mass of things like protons and electrons. You fire them by accelerating them through an electric field, and with a known electric field you will know how much kinetic energy they have after flying through it, being accelerated through it, and then you subject it to a magnetic field, and the curvature of its motion through the magnetic field is going to depend on its mass through Newton's second law. And from that you can determine the mass of things like a proton, an electron, or you can even measure the mass of a molecule that way, but that molecule has to first be ionized because a magnetic field and electric field only act on a charged particle.